Um, He's Dr. Kim from the Ewha Women's University, okay, in Seoul, Korea. And he's going to talk about resistive switching mechanism of single-crystalline oxide-based Schottky junctions.
Hello, I'm Dong-Wook Kim from Ewha Women's University. I will talk about the resistive switching behaviors of single-crystalline oxide junctions. And all these are my students and postdoc, and I also work with Dr. Hong at Argonne National Lab. Before starting the scientific discussion, shortly I will introduce Korea and also my institute at first. Now we are here, is it correct? Do you know where Seoul is? Somewhere. Right. Actually, this is Japan, big island, and this is China, another big country. In between here, the Korean Peninsula. I can see the brightest spot is Seoul, the capital of Korea. And as you can see, there are lots of bright spots that corresponds to big cities, Tokyo and Osaka and so on. So can you find any special relationship between these two cities? Yeah, correct. Actually, if you can check the coordinates, you can see that. When I was a student in elementary school, my teacher told me that if we make a hole through the center of the Earth, then we can reach the Argentina. It's correct, right? So, for example, now it's 3:20 p.m. here. And now in Korea, it's 3:20 a.m. So I don't have to adjust my watch. I can just read that. And, And also, before I come here, so the temperature in the morning is -10 degrees Celsius. Now it's 30, so winter and summer, all things are opposite. So if you want to see the other opposite side of the Earth, please visit Korea.
Actually, there's an app you can watch through the Earth.
Ah. Thank you. And at the center of the Seoul, our university is Ewha Women's University. Actually, Ewha means the pure blossom, and women's, actually that is not a typo. It means that the early founder of the university do not like the word women. Women doesn't contain any respect to individual women, so they made the word woman plus S to express the respect to every individual woman. And the university was built about 126 years ago, and we have a really big school. As far as I know, this is the world's largest female university. As you can guess, in a long time ago, the opportunity for high-level education to women is quite limited. So we can find a lot of alumni in many first in Korean history, the first a medical doctor, and also PhD, justice, prime minister, and so on. And still, we have a lot of great students, highly motivated and high-quality students want to study our university. So our rank is not that bad compared to other co-educational schools. Is really doing good. And also, there are important numbers here. Okay, then let's start the scientific discussion now. This is an outline of my talk. At first, I'll talk about why I choose single-crystal Schottky junctions, and then I will talk about two main approaches, macroscopic and nanoscopic characterizations. And also, in both of these studies, I will talk about ambient effects. And then I will wrap up my talk. Okay, as you already see this slide so many times, this is a famous figure of Dr. Sawa. And in both types of switchings, everyone knows that oxygen vacancy is really important. It's mobile dopants, and it can cause a computational variation, Locker error, so that corresponds to conducting filaments. And also, we can expect some local heating, Joule heating. So the Joule heating can accelerate all both this kind of migration and drift of dopants and so on. Actually, around 2005, I started research on RAM using thin film metal insulator metal structures. At that time, as you know, the Samsung is really extensively working on nickel oxide thin films, so I chose nickel oxide at the time. I compared two different films, identical structure, platinum, nickel oxide platinum structures. The only difference is the left-sided polycrystalline thin film and right-sided epitaxial thin film. You can see there's a big difference. In the epitaxial thin film, the switching yield is quite low, less than 50%. But in polycrystalline, all of them shows very stable switchings. With the help of the theorist, we get some first principle calculations. We can explain this difference due to the migration energy of oxygen vacancies along the grain boundaries. And also, we observe interesting switching behavior depending on the electrode materials. Actually, we chose silver and nickel oxide, and there's a very interesting alloy phase, silver and nickel. I'm sorry, platinum and nickel. And alloy, in the case of silver, they can diffuse into the nickel oxide. So the switching is not that stable. So from these STM studies, we can clearly reveal the existence of small amount of silver embedded in the nickel due to the difference of topographic images and also IV spectroscopy characteristics. So both of these studies, I realized that in thin film cases, it's really difficult to reach a good understanding of mechanism. It really depends on the materials and also the structural qualities and the combination of electrodes and so on. Most of these things are due to these two latter aspects, right? However, in single crystals, we can focus on the first thing. Mainly the vacancies can play as a role of mobile dopants. So I think that the single crystal junctions can be a good model system to understand the switching mechanism. And in addition, the insulated metal structures can be regarded as three resistor elements, the top and bottom contacts, and also the bulk. So if the bulk resistance is smaller than the contact resistance, mainly the resistance of the device is determined by the contact properties. Actually, yesterday, Dr. Sawa talked about the ferroelectric type diode devices. In that case, even though the structure is MIM, mostly the switching behaviors should be understood based on the contact properties. So everyone will agree with that. The contact is really important. So this is one of the first our research, and we studied the platinum strand tight and Schottky junctions, and this shows very stable bipolar switchings when you use high work function metal electrodes. And it shows good retention and endurance characteristics. Although the system is pretty simple, and we use a single crystal, however, we still haven't reached a very clear understanding of what is the dominant mechanism. Some people believe that oxygen vacancy migration and resulting variation of the barrier height or depletion width change is important. And also some people believe that the carrier trapping at the interface trap states are more important. Well, these two works are reported by Dr. Sawa's group. So I'd like to understand what is really important. So at first, I measure the barrier height using internal photoemission spectroscopy. It's a very simple technique. We use a photon. If the photon has enough energy to overcome the barrier, we can obtain the photocurrent. And the photocurrent response is determined by this equation. So we can read intercept in the horizontal axis, we can estimate the barrier height. And when we prepare the sample with different resistance states by using different polarity and different magnitude bias voltages, in all cases, the barrier height is nearly the same. So we cannot observe any change of the barrier height. However, as you can imagine that from the IV characteristics, we can observe a large change of barrier heights. So what is the reason for that? Actually, the answer is pretty simple. When you use IV techniques, if there is any inhomogeneity of the barrier, we can regard as like a parallel connected resistor problem. So the smaller resistance will dominate the total resistance. Okay? So if there is any small barrier height region, this region will determine the apparent barrier height. As a result, we can obtain the large change of barrier heights. But actually, if there is no big changes in the average value, for the current will be proportional to the area, so we can estimate the mean barrier height. So this difference means that inhomogeneity of the barrier height. And also we understand the transport mechanism. In the HRS case, this is the inverse slope of the IV and the temperature curve. If the transport is dominated by the thermal emission, this curve should be linear according to the simple equation. However, if the tunneling is important, then the IV characteristic will looks like this. Okay? So here we can learn that LLS state doesn't follow thermal emission behavior, and HRS looks like more like a thermal emission. So this means that in the previous slide, I estimate the barrier height based on the simple Schottky diode equation. Actually, that equation is derived from the thermal emission theory. So the barrier height taken from this analysis has actually no meaning at all, because the tunneling is involved. We cannot estimate the barrier height. Okay? So from all these results, I can propose this kind of cartoon to explain the mechanism. In both HRS and LS, barrier height doesn't change quite a lot. However, in LLS case, somehow tunneling transport is allowed, probably due to the very local area of barrier height lowering or deposition width change and so on. So this is a picture that we can propose to explain the switching behaviors of STO Schottky junctions. So I don't have to, actually here I can propose this kind of illustrations, but I don't say anything about the switching mechanism which can lower the barrier height, right? So I continued another experiments. Here I compare the switching behaviors in air and vacuum. At first, the switching is not that clear, blue one. And if you put the sample in vacuum, switching is quite clear, much clearer. Its width is much bigger. And then we come back to the air, switching is more like a previous one. So it's a reversible change. So how to explain this? We have two options. The first one is the oxide migration picture, and the other is a trapping picture. Which one will be more better? I should give you notice that actually the switching behavior sometimes doesn't change quite a lot in both air and vacuum. But sometimes we can see quite a big change. You can see what is the main difference of these two samples. The left one over the current level is much higher than the right one. So actually the left one is as grown sample. The right one, I annealed that at 300 degrees C. So I can reduce the amount of defects at the interface. So it looks like that in the change of the ambient in the vacuum environment can generate some defects. It looks like that. And also these two results suggest that the trapping scenario will be better. So next issue is how to prove the existence of traps. So I learned one interesting model proposed by Nicolai and Gasberger in 1967. They proposed this kind of interpolated trap space study model for MIS structures, metal insulator semiconductor capacitor structure. So actually here we have one capacitor and the insulator capacitor, and another one is a depletion width capacitor. If there is many traps, we can store the charges even at the traps. So that will give additional parallel capacitor component. And in addition, we can fill the traps, and the charging and discharging corresponds to some conductance component that is here, right? And this can have the equivalently corresponds to this circuit. So our Schottky junction case, actually, we already know that interfacial layer can exist. Actually, Dr. Hall also mentioned that this issue yesterday. And there's one old paper, and also we found that our device really have interface layer from their CV characteristics. In order to explain the built-in potential, we should include interface layer. So even in the case of Schottky junctions, that can be modeled by this kind of equivalent circuit. So this shows the result. And we can find features from this conductance versus frequency curve. This means that the trap states model to really work. So our device really have interface trap states. And the peak position will give us the tau, the characteristic velocity time. So the thermal average velocity in cross-section and intrinsic carrier concentration. And US and UV indicates the difference of the surface band bending and the Fermi level and intrinsic level difference. So roughly that corresponds to the surface band bending, this term. So here you can see that the LRS state has a higher peak frequency. And also in vacuum, the peak frequency is moved to the right side, higher frequency, right? Both in air and vacuum. So what kind of conclusion can be reached from this result? That basically this kind of picture is already known. However, the detailed explanation is a little bit different. And to explain this kind of change of surface band bending, we can explain this is mainly due to this kind of surface band bending, and it's due to the trap states. We don't have to say about oxide vacancy migration. We don't need to that. And mainly this kind of LRS and HRS states difference, also the similar found in vacuum air data. This means that the trap states are strongly affected by the ambience. Okay? So I'll talk about this ambient effects again later. So from this result, we can say that trap states are really important in the resistance switching behaviors of our Schottky junctions. So as I told you, there are two pictures. We believe that the second one, the trap picture, is more important, at least in our device. Okay, up to now I talk about some macroscopic characterizations, and still we want to see the actual interface. Okay, so we prepared the planar junctions instead of the conventional vertical junctions. Here we can see directly the bulk region and the contact regions. And here is example images. We deposit titanium electrodes to form ohmic contacts, and the other side of the platen is the Schottky contacts. And from this device, we can measure the IV characteristics. And at the same time, we can characterize the surface by using AFM technique. So we can clearly understand the contact and bulk contribution to the total resistance. And also we can get clear idea about the Schottky and ohmic contacts and in real space observation. So this is one of the results. This is the microscopic image of the device. When I apply the minus 40 volt to the platinum electrodes for 30 minutes, you can see that there is a reduction of the resistance. So it looks like that this kind of change can be explained based on the oxygen migration picture. Okay, we put the negative bias to the platinum electrodes. Oxygen vacancies can be accumulated at the interface. Okay. However, when I apply the positive bias voltage, also I can observe the decrease of resistance. So we need some more oxygen migration picture cannot explain these two results. So here I can obtain the surface potential maps. So from this we can estimate the contribution of the contact and bulk resistance. And initial device, there is a large voltage drop at the platinum titanium oxide interface because it forms a Schottky contacts and very small contact resistance from the titanium contacts. And the other portion corresponds to the bulk resistance. After applying minus 40 volt, there is significant decrease of the contact resistance as expected. And plus 40 volt case, the contact resistance doesn't change quite a lot. However, we can observe quite a big change in the bulk resistance. Actually, even for minus 40 volt case, there is a decrease of bulk resistance. So the issue is how to explain the bulk resistance change. Okay? Basically, the Schottky contact portion is already explained that basically the main idea comes from the PT-STO case. Whenever it's the oxidation vacancy model or Trapezoid model, we can explain that. So the issue is the bulk resistance change. So to see what happens there, I obtained the work function maps in this junction area. The reason to measure the work function is because we can get some idea how the carrier concentration is changed. This is an N-band diagram. If there is any change of the carrier concentration, that will change this value, and as a result, work function should be changed. Okay? So for example, when I apply minus 40 volt to the platinum electrodes, if the carrier concentration is increased, the work function should be decreased. Okay? However, the result is opposite. Work function during the platinum electrodes increased. Okay? And moreover, in all the bulk region, the work function is reduced. So we cannot explain that based on this carrier concentration contribution. We need another mechanism. But that is due to the oxygen absorption. Okay? I already talked about some absorption is important Trapezoid contribution in the previous PTSTO cases. Also here is very important, this portion. If the oxygen is absorbed at the surface of titanium dioxide, it's pretty well known that the oxygen will take electrons from the TiO2. Okay? So the carrier concentration is reduced at the surface. That will cause the surface band bending. And in addition, this negative ions will form dipoles. So all these will change work function. So this is a scenario to explain all the experimental results. This is the initial sample stage. Actually, we anneal the sample in a forming gas environment for a short time. So only at the surface is high carrier concentration. So it's like a single crystal thin film. And if we put the sample in vacuum, the oxygen gases will absorb. And as I told you, they will deplete the surface region. And also, the carrier depletion can be expected under the platinum electrodes. And after applying the minus 40 or plus 40 volt, somehow the amount of absorbed gases is reduced. So that will cause the work function change in the bulk region. Okay? And just under the electrodes, actually, I have no idea because I cannot get the work function information under this area. But in the minus 40 volts, somehow the amount of the gas absorption doesn't change quite a lot. So this is a picture that I can propose. So according to this picture, I can explain all the resistance change behaviors. The important thing is that all these experiments, even in the previous cases, the gas environments are really important. They can affect the actual carrier concentration at the surface region. This is a very important message from both of these results. And it's quite clear that if you put the sample in the vacuum, the current level is quite increased quite a lot. Okay? That's pretty obvious. There are a lot of studies about the gas sensor applications of N-type oxide semiconductors. So from up to now, I found a lot of interesting results, but still I have no idea what really happens under the electrodes. Okay? So I tried another experiment here. So with the electrodes, I cannot find any information at the electrodes and semiconductor interface. So I have no option anymore. So I should remove the electrodes. And instead, I use a conducting AFMT as a moving electrode and apply the bias voltage for a while. And then I obtain some electrostatic images at this area. So let's see what happens. This is the obtained the results at 3 different gas environments. Just before I talk about the ambient effects is really important, so I compared 3 different gas environments. The quite clear difference can be found in the reduction ambient hydrogen environment. And this is a photograph images, the schematic procedure experiments. To control the environment, we use a very tiny cell, and we can compare the three different gas environments. So this is the profile of amplitude and phase. In this kind of EFM images, this amplitude and phase corresponds to these quantities. The amplitudes will give us some information about the magnitude of surface potential, and the phase corresponds to the polarity of surface potential. So only in the hydrogen ambient, the polarity of surface potential is changed. Okay. So to explain this, I missed one important point. Here, this is a scanned area by a T, but also we can see a clear difference can be found even in the unscanned area. So only we just put the sample in different ambience, something happens. Okay? So to explain this area, I measure the work function and I compare that in three different ambience. There's a clear difference can be found. And to explain this, I again use this kind of Ennis band diagram. I should include the gas absorption effects. So from these differences, I estimated the amount of oxygen gas coverage on the surface is roughly 4%. And from the literature, it's known that the oxygen gas is preferentially absorbed at the vacancy sites. And the oxygen vacancy amounts in this range after the similar heat treatments. So this value is really reasonable. So the work function difference shows that the area of the sample undergoes the oxygen absorption depending on the gas environment. So this is the scenario that I can propose from these experiments. And actually, before inserting the sample in the AFM cell, I heat the sample for a while to remove the water. So I only can say that the major absorbent gases are oxygen. So just after putting the sample in argon ambient, still we can expect some remaining oxygens. But then put the sample in oxygen, maybe the more oxygen can be absorbed. But if you put the sample in the hydrogen ambient, we cannot expect most oxygen will be removed. Okay, this is the before this is initial stage. When I apply the positive bias T, in the first case, we might have a chance to remove the oxygen from the sample. But in the latter two cases, maybe we can remove only the absorbed gases, oxygen gases. And especially in the oxygen ambient, there is a lot of chance to the reabsorption of gases, oxygens, because there are lots of oxygens around. Okay. So from this result, we can see that it's really hard to compare the AFM measurements with the real MIM structures because there is a big difference, and the really ambient is really important. So here I show you that these three different cases can be obtained to control the environment. But if you carry out the similar experiment in just atmospheric pressure, there is a large change of water level, humidity level. So everything is quite complicated. So we really should be very careful to explain the experimental results. That's an important message. And the last thing is just a demonstration of how small side nanocontacts can work as a resistive switching devices. So here we put the electrodes using a nanosphere lithography technique. You may have heard about that. We can put some nanospheres on the sample that will form closed packed structures. And the exposed area, we can deposit electrodes. They have a hexagonal symmetry. And after removal of the nanospheres, we can form very tiny metal contacts. And from this kind of small side contacts, we can observe clear switching behaviors. Actually, this experiment was done in ultra-high vacuum environment, 10 to minus 10 torr vacuum level. So we cannot expect any environment effects at all. So even though in such cases we can get clear switching behaviors, so I should say this switching is mainly due to the electron trapping effects. Okay, this is a summary of my talk. In the first part, I mainly talk about the PTS to Single-Crystalline Junctions, and I believe that the charging and discharging of interface traps is really important. And these trap states are affected by the oxygen absorption. So ambient effects is really important. In the latter part, I showed some AFM studies. In this case, it's also the oxygen distribution is really important in determining resistance states. And also, we can learn that SPMT is really a powerful tool to modify the local surface charge distribution. So, from all these results, you may ask me how this kind of result can be applied to the thin film cases. As I told you in the introduction part, still there are lots of complications depending on the material, the compounds, the detailed microstructural properties. But I can say something like this. This kind of switching is mainly due to the trap states, more like an electronic process. So that corresponds to some ignition process in thin film switchings. So once this kind of switching can occur, it can form a conductance chain, and as a result, joule heating can occur, so they will accelerate the migration of oxygen vacancies along the defects of thin film devices. So this is my students and research funding. Yeah, this postdoc, he's man, all others are female students. Thank you very much for your kind attention.
This session is now open for questions.
Can you move to the slide 13? I have a question on the IV curve and the deeps at low current levels. Do you have a... Yes.
Actually, this is like a relaxation behavior. You can see in the left-hand side, there's no deep like this. This is more conducting sample. So this is more like, behaves like a resistor. At the right-hand side, that sample is more insulating. So still we can expect some capacitor-like behavior. So this corresponds to the kind of charging, discharging current.
I'm sorry, I disagree with that. I'm sorry, I disagree with that. I disagree with that, I'm sorry. The reason why you see that is because there's an offset current when you measure. When you take the log, that's what happens. So if you remove the offset current at zero bias, then that thing would disappear.
Correct?
Offset current at 0 volts, when you do that measurement, then you see a little bit of current. At 0 volts, there should be no current, unless there's a real current. That's all I wanted to say.
Yeah.
You see a lot of that.
Yeah, okay.
If there's an offset current.
I will explain in a different way. So, yeah, as you pointed out, this is actually absolute value current at low scale. So if we draw the picture in the linear scale, then you can see that the sign of the current is changed at this point, right? That means that even 0 bias voltage, we can observe some current. So that is the discharging current of the capacitor. That's my explanation. So I can understand the offset current idea.
Correct. Now, if you look at negative current, negative bias, you see positive current.
Yeah, so that's a discharging current. So the kind of behavior depends on the switching speed.
But it happens if you don't offset properly. So it's just a measure of current, but it could be an offset problem in your measurement apparatus.
Yeah.
I've seen that many times, and usually depending on how you set up your measurement apparatus, you see in some and you don't see in others.
If I mention about the error, the current error in this measurement is pretty much lower than this value, so we can measure at least at the equivalent point of view, we can measure the actual current.
Any other question?
What is the volatility of this load?
Sorry.
What is the volatility of, can you estimate the volatility
Yeah, I show you the retention characteristic before. Retention endurance characteristics. It's a really non-volatile memory.
So you showed in your model, you showed the partially, the locally, potential profile, the Schottky barrier, decrease. So, but I think your results can be explained by the other model. So the locally, the Schottky barrier width thinner. So this case also the internal photon emission show does not depend on the resistance state.
So, as I explained in the previous slide, actually,
Yeah. So
in
this case, you showed some part the Schottky barrier decrease, but if you consider the partially the Schottky barrier width thinner, so that case also this model can explain your experimental result, I think.
yeah, so actually it's not easy to estimate the barrier width, right? So I cannot deny such a possibility, but usually according to the general semiconductor physics point of view, the width can be changed by the amount of the carrier concentration. So if so, the overall picture is quite complicated. So
no more questions? Okay, so we thank Dr. Kim again, and we have